spent quite a bit of time establishing that resting membrane potential, now we have to maintain it. And the maintenance of the resting membrane potential is what we call the pump leak system. So we've got sodium, potassium pumps on the membrane that are pumping sodium and potassium in their respective directions. And then we have that being balanced out by the leak channels that are leaking those ions according to their concentration gradient, okay? And so that's what maintains the resting membrane potential after it is established at first. And so here we can see that the resting membrane potential is closer to the potassium equilibrium potential. So this is what I was trying to point out a bit earlier. So the resting membrane potential being -70, not only is it also negative, right, just like potassium's equilibrium potential, but the value is also similar as well. And we said that the reason for this is because we have more potassium channels, and so potassium can move more freely in the cell than sodium can. And we also can see how far away sodium's equilibrium potential is from where the cell is at rest. And that also reflects the magnitude of the force with which sodium wants to move. So because it's so far away from its equilibrium potential when the cell is at rest, then sodium really wants to get into the cell. And the magnitude of the force with which sodium wants to move is equivalent to the distance the distance or how far away sodium is from its equilibrium potential when the cell is at rest. And we can see that that's really far for sodium and really close for potassium. We can also see that the direction is different. So sodium is going to have to move into the cell to get to its equilibrium potential, right? This is positive. Whereas potassium is going to have to move out of the cell to get to its equilibrium potential, which is negative. So just going back to that question that I got over the weekend about whether or not two ions could be at equilibrium. So if the membrane potential is not at equilibrium for an ion, the ECDF is not going to be 0. And if the ECDF is not 0, we will see ionic movement. Remember, when the ion has reached its equilibrium potential, another way to say that is when the membrane potential of the cell is the same as the equilibrium potential of that ion, then there will be no movement for the ion. Until then, the ion will be moving in a direction that will try to bring it closer to its equilibrium potential. So the net force that's moving our ions is a force that's trying to get them to be at equilibrium, but they both cannot be at equilibrium at the same time. And so when the cell is at rest, it's an in-between ground between both of those ions. And the second point here is that the strength of that net force is going to get larger the further away the membrane potential is from the equilibrium potential of that ion. And another way to say this is the strength of the force that wants to move, for example, sodium, is larger because the membrane potential at rest is really far away from sodium's equilibrium potential, whereas the strength that wants to move potassium is smaller because the membrane potential at rest is closer to the equilibrium potential of potassium. Okay, so we're pretty much just reiterating that concept here. We talk about the resting membrane potential being -70. We talk about potassium's equilibrium potential being -94. And so the membrane potential is going to be 25 millivolts less negative than the equilibrium potential for potassium. What that means is that the electrical force is going into the cell, the chemical force is going out of the cell. And so we subtract those forces because they're in opposite directions. And so we get a smaller value, which is 24. And the general direction is going to be out of the cell, but very weakly so. So it's going to be like potassium is trickling out of the cell. Looking at sodium again, we look at the equilibrium potential, which is +60, so way on the other end of the spectrum. And now what we do is we add these values, right? So we're going to add that -70 to that +60. And that gives us 130 as far as the value, as far as the magnitude or the strength of that force. And so this shows us the force with which sodium wants to get into the cell. It really wants to rush into the cell. It has a strong combined force when we look at the electrical force and the chemical force, since they're both in the same direction. Okay, so we now have a small amount of sodium leaking at rest because of the low permeability. And then we have a small amount of potassium leaking at rest because of the high permeability. And we've also got the sodium potassium pump just kind of keeping things maintained at that level, right? Keeping the relative ion concentrations, keeping the inside of the cell negative at rest, keeping the outside of the cell positive at rest, keeping a higher concentration of sodium outside and a higher concentration of potassium inside. So all of this is just being established by this pump leak system, the combination of the sodium potassium pump and the leak channels for our respective ions. Okay. So I want you to pause and think about one question that you may still have lingering. So as we wrap up speaking about the resting membrane potential, we're really going to build on that and talk about the action potential. Okay, so before we kind of move on in a hurry, I really want us to spend some time making sure that we don't have any questions about the movement of our ions, sodium and potassium, and about how we get to that -70 at rest. Okay. All right, so I'll give you a minute to think about a question. If you don't have a question, that's okay too. If you do have one later on, you can email me. If you do have one now, you can share it in the chat. I'm not going to respond to them right away, but I'm going to just collate them or collect them together and address them the next time we meet. So if you've got a question, you can put it in the chat, even though I move on, and I'll have a look at them at the end of the session. And if you don't have a question, that's okay too, okay? Okay, so we're gonna keep going here. Also, there's a really interesting, really nice video that I've put in Brightspace that could help simplify some of this. So if you're having a hard time, definitely check out that video, in addition to reading up in the text as well. If you're struggling with this information, please reference videos or the text that can help to clarify some of these concepts that we're talking about. So here is where we kind of bridge the conversation from the resting membrane potential to speak about an action potential. So before we get to talking about what an action potential is, an action potential, let's just describe it here a little bit. It's kind of an explosion of electrical energy that is used to signal from one cell to the other. So you've heard me talk about these excitable cells. Neurons are an example of excitable cells. Muscle cells are excitable cells, cardiac muscle, skeletal muscle, smooth muscle. Some endocrine cells can also be excitable cells. But an excitable cell is a cell that has the ability to generate this spontaneous burst of electrical energy in order to send a signal to another cell of that type or to another excitable cell. So a neuron, excuse me, a neuron can generate an action potential, which is where we have a deviation of the membrane potential. And so we can see here that at rest, the cell is at -70, but when we fire an action potential, the membrane potential rapidly becomes more positive and then rapidly becomes more negative. So this rapid spike in the membrane potential is what we call an action potential. And the reason that cells do this is to be able to pass messages from one cell to the other. So they're basically, in a very simplistic way, an action potential is the language with which excitable cells use to communicate between themselves or across themselves. And I want you to take a guess. So take a guess on this in the chat. If we have the membrane potential becoming rapidly positive, which ion do you think is moving to create this membrane potential change? Which ion do you think is moving to initiate an action potential or to help the membrane potential become so drastically positive? If you were to take a guess between sodium and potassium, which of those two ions would you suspect? Excellent. So I'm seeing a lot of response for sodium. Perfect. So that is absolutely correct. So sodium is what moves. Remember, sodium is trying to get to its equilibrium potential. That is the force that's moving sodium. So it's going to rush into that cell. And so the membrane potential is going to spike and start becoming more positive as it tries to approach the equilibrium potential for sodium, which is really positive, positive 60. It doesn't actually get there, but it gets really close, right, at positive 30. And then we have the movement of another ion. And as you would probably imagine, that's going to be potassium movement, which brings us back down to our negative 94, which is potassium's equilibrium potential. And then eventually we get back to the resting membrane potential. So that's in essence what an action potential is. And so we're going to spend some time in our following packet, in the action potential packet, speaking about how we go from rest to exciting the cell and firing an action potential.